Good morning, I'm Ben Cohn, and today we're talking about separation of variables. So we've already gone over a few techniques. This is another technique. I'm going over it at the end though because it's not really a core technique that you'll come across very often, at least not in this class. But it's kind of good to know that it exists and kind of the implications of it. So for example, we're given this guy right here, and we're asked, all right, find the integral of this, or find y of x, so to speak. Oh, ooh, red. The question is y of x equals question mark. So the goal of separable equations is you want to get all the y's on one side and all the x's on another side. So we would rewrite this as 1 over y squared dy equals x dx. Now, you really aren't supposed to separate the dy dx like that. The dy dx is the derivative of y with respect to x. And you really can't say, well, dy is a small portion of y, dx small portion of dx, and then integrate both sides. I do that all the time. And this is kind of an abuse of notation. True. It doesn't bother me. And you shouldn't really let it bother you, at least not at this point in life. When you continue on with your math career and you get higher up in the circles of math. Do they have circles of math? Why do they choose circles? You think that mathematicians would have a more complicated sort of thing. The manifolds of math. Ooh, I like that. The inner manifolds. Okay, totally tangential. So the idea here is you're not supposed to do that. It's okay. It's more of a mnemonic to rewrite it this way, to separate the dy and the dx, and then go from there. That mnemonic, totally fine. You're okay with it. Pretend it's good. It's good enough. No one's going to care. And you always get the right answer anyway. So go with it. It's not to say you aren't supposed to be careful with how you do this. So we have this situation. We write it like so. You don't have to actually change the color to green. I mostly just do it because I like it. We write it like so. Y goes to the negative 1. Take the 1 divided by the negative 1 equals x squared over 2. And I'm going to say plus c. Now you might be thinking, why did you put the c on the x side and not the y side? It doesn't matter. I could do c1 here, c2 here, and then rewrite it as c2 minus c1 on this side, and then say, well, a constant minus a constant is just another constant. And so it's easier for me to write the c2 like that. Now, with some cases, you kind of have to be careful. So the idea is keep your head on a swivel, look at what's going on. But especially for things like this, you're pretty fine. When you get to doing exponentials, sometimes you have to be careful about the constant because it gets multiplied when you simplify the equation. But for this, you're fine. So we have negative 1 over y equals x squared over 2 plus c. I'm going to simplify this to x squared plus 2c over 2. The idea is I multiplied the c by 2 over 2, which is 1. 2 over 2 is 1. You can always multiply by 1. That way, when I invert it, I have y equals 2 negative over x squared plus 2c. Okay? And then, again, before, you could say, well, this is really c3, and I'm going to say that this is c. I kind of abuse constants almost as much as I abuse notation, but it's actually more legitimate for me to abuse constants this way because it's just a constant. So, like, if C3 here was, from negative infinity to infinity, non-inclusive, Then if we double it, we'd get negative 2 times infinity to 2 times infinity. Well, there's one thing you learn being a kid and calling your friend poopy head times infinity, and then he calls you poopy head infinity times plus 1 or whatnot. It's really all the same. So 2 infinities and 1 infinities, same infinity. So everything that's included in 2c3, 2 times constant of 3, would be the same as another constant. And so that's why it is actually completely legitimate, as opposed to many things that I do, to say that 2c3 is just c. And so here we'd say y equals negative 2x squared plus c. Yep, I'm good with that. So now let's go on to another example. So looking from our strategy for the last one, same idea. Get the y's on one side, I'm going to say the left. Get the x's on the other side, I'm going to say the right. Integrate both sides. That was pretty well choreographed. And then once you get to integrate, simplify how you like, and then that's your y equals x. So same concept here. We're going to do, let's see here. This one looks a little bit easier, and it is this one is pretty straightforward. So we have y dy equals 4x dx. Integrate, y squared over 2 equals 4x squared over 2 plus c. That'll be 2. Okay. Y squared equals 4x squared plus c. It's really 2c, but I'm going to just round that to c. And so then we could say that y squared y equals 4x plus c square rooted, which is probably fair, but let's say that we had some initial condition, etc., where we knew that the c equals 0. So we're just looking for a solution, not all possible solutions. So it's going to be square root of 4x squared, which would be 2x. Okay, so we come down to y equals 2x. So there's some things you really kind of have to worry about here. So if your spider senses are going insane, that's probably fair. So before we had y squared equals 4x squared, and now we have y equals 2x. Well, for this, we could say y equals negative 2, x equals 1. But then we go down here, and we have negative 2 equals 2 times 1, question mark? Does not. And the idea here is when we took the square root, we lost information. That's why a lot of times you'll see like an absolute value signs, but it really comes down to, as we did this, we lost information. Another thing to look at is, well, if we say this is our equation, then 0 squared equals 4 times 0 squared. Well, that's true, but y can't equal 0 because we're dividing it. And so if this is our beginning base of everything we know in life, when we step off from there and move on out into the wilderness to make our way, we can't forget that from the beginning, y cannot equal 0. So this equation we have up here with y squared equals 4x squared and later y equals 2x, those can't be entirely correct because we lost information. Another way to view this is blue. If we look at this, so if we look at this solution right here, now just draw it. this solution right here is something like this. Y equals 2x. Where the correct solution is something more along the lines, line to get it because it's, never mind, not important. Something like this. And then there's make a little circle there to show that y cannot equal 0, which also means x cannot equal 0. And so what we did was we found this solution, but really the solution we were working with was this guy right here, the cyan blue one. And so one of the things you really have to be careful about is as you're moving through this, you can be losing information. And you could start saying and asserting and writing down things that you assume to be true, but actually aren't. You can make hard, fast rules where, well, when this happens, you have to take into that, etc., etc. I find it's better just to kind of attune your spider senses to things that feel wrong. Well, feel dangerous. So when you are dividing by a variable, you should automatically think, all right, this variable can't equal 0. And when you square root things, you have to think, all right, this goes from a negative number squared going to a positive number to when you square root it, you have a positive number or a negative number that will then equal a negative number. And so you have to be kind of aware of that information that can get lost. And a lot of that then just comes down. I try to use it as common sense as you're going through. I know, like, well, just use common sense. Terrible advice. Truly terrible advice. But yeah, it's pretty much, you work problems, you look at things, and after a while you're like, all right, this is where I'm losing information, this is where I have to be careful. So that's the general idea behind separation of variables. Clean this guy up real quick, and we'll look at another example. Okay, so here we have an exponential. Lock this guy into place. So we have e to the x plus y. Now this equals e to the x times e to the y. Because when you add them together, the exponents, you can then separate it into two separate bottom of the exponent, the thing that's being exponented. But when if you had x times y together like this, multiplied, then that would equal e to the x to the y, which would equal e to the y to the x. And one of the ways that I remember that is I use 2 and 3 for everything. So you can think of, let's say, e to the 2 plus 3 equals e to the 5th, which equals e times e, this is 2, e times e times e, this is 3, which equals e squared e cubed. And so I can go through this process and be like, okay, that all seems pretty reasonable. And if you want something even simpler, you can be like, well, 2 to the 3rd, I know equals 8, which equals 2 to the 1st times 2 squared, which is 1 plus 2 equals 3, equals 2 times 4, which equals 8. So yes, warm fuzzies initiated. So that is true. So then when we separate the variables, so to move a variable to the other side, with an exponent like that, we'll multiply by e to the negative y. So what we do is we have e to the negative y dy equals e to the x, e to the y, e to the negative y dx. Where when you have a negative exponent, you can write it on the bottom, like so. E to the y divided by e to the y is 1, which equals e to the x dx. Pretty reasonable. Okay, we're good with this. So we have our variables separated. Integrate, integrate. So I'm pretty sure this is just e to the negative y over negative 1. But I'm never entirely sure about these things. So to actually do it, I'll do it through substitution. So u equals negative y, du equals negative y, negative dy. There we go. Therefore, negative du equals dy. So then this goes to integral e to the u du negative. Okay, I'm good with this. Which is e to the u negative, which equals negative e to the negative y. Okay, so it's just the negative goes down. I've done that probably a million times. I think I would know it by now. I find that I often know the right answers, but it's when I know the wrong answers but think they're right, that's when I get in trouble. Negative e to the negative y equals e to the x. Okay? Solving this for y, let's do e to the negative y equals negative e to the negative x. We'll do 1 over both sides. So 1 over e to the negative y equals e to the y, which equals negative 1 over e to the x, which equals negative e to the negative x. Taking the natural log of both sides, we have natural log of e to the y equals natural log of negative e to the negative x. I have to be careful because when I write quickly, sometimes my x's and y's look the same, which completely defeats the purpose of having separate x and y's. So we have y equals natural log. Ooh, did I forget I think I forgot a constant. I forgot a constant. Outrageous. Plus c, and then that's within the natural log. So then, is that true? Mostly true. All right, where did I take this? So plus c, which then becomes negative c, which is fine, I don't care. No, I think I'm going to have to go back just a little bit. Whoop. Erase this guy. Erase this guy. So we have, take the inverse, go back to red. We have 1 over e, negative e to the x, plus c. Take the natural log of both sides, and we have y equals natural log of negative e to the x plus c to the negative 1, which equals, I'll put the equals down here, equals natural log of e to the x plus c with a minus out here, y of x. So I was pretty loose with the whole worrying about things not being able to equal 0, the absolute values of things as required, and I kind of moved through that without paying attention to that. So I'd have to be really careful when I go back and make sure to see what the domain and range is. Domain is what value you can input, and range is what value you can get out. So in this case, domain would be the x value, and range would be the y value. So I was pretty loose with that. I'm okay with doing that because for the AP exam, for the most part, it's not going to be an issue. You'll be given, if you get a problem like this, you'll be given one where you don't have to pay too much attention to the domain and range. But if you do, then you'll be able to solve the problem, go back, look at your beginning, and pretty much figure it out that way. So I'm not saying you're completely safe to ignore all the pitfalls we showed in the previous problem, But for the AP exam, you're better off worrying about just the process. But like, okay, x is over here, y is over there. Integrate both sides, move on. And then you'll just move on to the next problem. So that would be how we'd solve this. We get y equals a natural log of e to the x. And then we have the c in there. So if we say that if for some reason c equals 0, then we get negative x, but that can be a little bit tenuous. So you might be given information that c equals 0, and therefore it collapses, but you can't necessarily assume that. And that's why you get the funny natural log and e to the x involved. Okay, clean this one up just a little bit. When you're first doing integrals, you're probably like, oh, that darn c, who cares about that c? Yeah, sometimes it's important. But, other times it's not. Okay, so here is another one. This is probably more like the sort of thing you'd see where you have multiple pieces and you kind of have to pull it together. It doesn't make it harder. In some ways, it kind of makes it easier. But the way you'd approach this one is be like, all right, well, dy dx equals x plus xy squared, which equals x, factor out the x, 1 plus y squared. And it's like, oh, okay, 1 plus y squared. And this is the part where you should probably break out in a cold sweat, because like, oh, how am I going to integrate that 1 plus y squared? Yep, trig substitution. Womp womp. I know. No one likes trig substitution. But this one, not that bad. So let's see here. We know when we add the two values together, we should say that y, usually it's x, but in this case it'll be y will be tangent of theta. dy equals secant squared of theta. And that's always the funny one. Like, you can figure it out pretty easily. Okay. You can figure it out by being like, well, y equals sine over cosine, and then using not the product rule, but the derivative rule, which I don't use because I think it's easier to just do sine times cosine to the negative 1 and then use the chain rule. And so I do everything with the product rule. And I don't use the dividing rule for derivatives. But when you're doing a test and they assume that you just know that tangent of theta derivative equals secant squared of theta, you don't have time to go through all that rigmarole. So it's just one of those things that's like, okay, memorize, write it down, move on. Okay. Delicious. I think I have a watermelon flavor today with extra electrolytes. So we have 1 over 1 plus tangent squared theta integral times dy, which is secant squared theta, equals x squared over 2 plus c. And is purple and green, I know, are those Louisiana colors, or is it like specific? Because I think that's associated with like Mardi Gras. You see a lot of that. But I don't know if that's also associated just with Louisiana, because every time I see, I should look that up. Not important. Okay. So we have 1 plus tangent squared theta. So you think, all right, sine squared of theta plus cosine squared of theta equals 1. Divide both sides by cosine squared of theta. We get tangent squared plus 1 equals secant squared. And I left off the thetas just for ease of use. And so this 1 plus tangent squared, okay, this is tangent plus 1. You can move them around. It's okay. Integral secant squared theta, that's a 2. Secant squared theta, d theta. There's a d theta in here. Did I forget the d theta? I did. That's a chain rule right there. Take the derivative of the outside times derivative of the inside, d theta. Cancel, cancel. Left with theta which equals x squared over 2 plus c, which I'm going to say is x squared plus c over 2. Make a squiggly line, sort of, kind of. You should not actually make a squiggly line like that. You should, if you're going to write that down, you should be more formal. I'm not formal. Though justified, it's one of those things where it's like, you do it, everyone knows exactly what you do, but they want you to hear you say that you did that. It's like, okay. Okay, so now we need to find out what theta is. So theta equals arctangent of y. And I use arc instead of that little -1 symbol because I get that -1 symbol confused with like the inverse. Ooh, inverse is not. The one, I get the -1 symbol confused with the idea of to the power of -1. That -1 symbol does mean inverse, but it's the sort of thing where when you're talking about multiplication, that -1 is the inverse because 3 is the inverse of -1, or 3 1/3 is the inverse of 3. But don't worry about it. Focus, back on task. Okay, so now we have arctangent of y equals x squared plus c over 2. And then we take the tangent to both sides, and we get tangent of x squared plus c over 2. And then you kind of have to be careful here about your domain and range, because tangent isn't defined for everything, and so you can set yourself up for not set yourself up for failure per se, but this right here, orange doesn't show enough contrast, insufficient contrast. This right here, y equals tangent of x squared plus 2, is not the same as dy dx equals x plus x times y squared. So depending on which kind of context you're asked to deal with, you should be a little bit careful. And that's the idea behind separation of variables and how you can use that to find a y of x given a derivative. Next time we'll go over polar coordinates and parametric equations, and probably cross product, dot products, which you probably already know, kind of, but I'll talk about just in terms of AP exam. And that'll pretty much round out most of what we need to know for taking the AP BC Calculus exam. So I appreciate you guys stopping by. I will see you next time.